Okay. 6.4b is the fundamental theorem of calculus, part 1. It's kind of a big deal. It's the fundamental theorem. And we are going to take those functions that we learned about yesterday, those accumulation functions, and take the derivative. That's what the fundamental theorem is all about. It's kind of a big deal because it's the fundamental theorem. Today is an example of a day when I want you to understand the math, because doing the math is actually not that difficult. So I'll show you the understanding piece. Just watch, don't take notes, just work on understanding it. And then I'll show you some examples and you will totally be able to do the examples. All right, so we are going to take that accumulation function that we talked about yesterday, and we are going to take a derivative of that function. So remember, here's a graph of f of t. F of t doesn't move. F of t is static. It's sitting there on the plane. T is not our independent variable. X is our independent variable because we are changing x by moving along the x-axis, along the t-axis, and then that gives us a different area. All right, so we're going to take a derivative of this function. So we're going to start by taking f prime of x. When we take this derivative, we're going to go way back to the definition of a derivative. So the definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x all over h. All right. So then, remembering that what the definition of f is, that means we're doing the limit as h goes to 0 of the integral from a to x plus h dt, minus the integral from a to x of f of t dt over h. All right, so far we've only used the definition of a derivative right here. And here we use the definition of f. Now, let's go back to our picture. The integral from a to x plus h is going to be the area of this pink part and the area of this little skinny bit here. So all together. So that's all the way out to a to x plus h. We're going to take away from that the integral from a to x. So we're going to take that whole big area and we're going to take away this bit. And we're left with just this skinny little sliver. And not only is it a skinny little sliver, but it is infinitely skinny because we have the limit as h goes to 0. Okay, so we can approximate that skinny little sliver as a rectangle. And so we're going to look at that skinny little sliver as a rectangle. The height of that rectangle, so anyway, I'm going to back up a little bit. This limit is going to be the area of, I don't know what to call that sliver. And the reason it's the area of that sliver is because from a to x plus h would be all the way out here. From a to x would be to this far. So if we subtract, then we get just the sliver. So it's the area of the sliver divided by h, and it's the limit as h goes to 0. Sorry. So what I want to remind you about is the area of that little tiny sliver is base times height. So the base of that tiny sliver is h, and the height of that tiny sliver is f of x. Or f of x plus h, but since they're little tiny, midpoint MRAM, RRAM, LRAM doesn't really matter because their slices are so tiny. So the area of the little tiny sliver would be f of x times the width of the little tiny sliver, which is h. You see where I'm going with this? These h's are going to cancel. And so we're left with f of x. And one thing that's kind of confusing is that we have a big F, which is the function that gives us the area under little f. When we take the derivative of big F, we get little f. The thing that's fundamental and kind of mind-blowing about the fundamental theorem of calculus is that we had these two ideas. One idea is the slope of a tangent line. It's the slope of a curve. And we'd really like to be able to figure out slope even if our line is not a straight line, right? So we developed derivatives in order to figure out slopes to curvy functions. And then separately from that, we're taking the area between a curve and an x-axis. And so those two ideas feel really different. One of them is looking at the rate of change, one of them is looking at the area under a curve. And the fundamental theorem of calculus basically says, you know what? They're not that different. If we go back to this equation here, if we take the derivative of both sides of this equation, then the derivative undoes the integral, and we wind up back at f. So the derivative and the integral are basically inverses of each other. And so that is a huge idea where slope and area don't seem like they're related all that much, but if we take the derivative of this kind of accumulation area function, we wind up back where we started. That is the first part of the fundamental theorem of calculus. I will put it in words. This part is on your note sheet. If your function is a continuous function over an interval, then if little f is a continuous function, then we're going to define big F as the accumulation from a to x underneath that curve. And we're going to say big F is differentiable, and if we take a derivative of big F, we get little f. Okay. So let's use it. Here's an example problem. F is the accumulation of area between 3 and x of the sine function. So when we take the derivative of big F, we get sine of x. And if we want to know what f prime of pi over 4 is, then we need to evaluate sine of pi over 4. And sine of pi over 4 is root 2 over 2, so that's our answer. Here's a second example. Go ahead and pause, try it yourself, come back, check your answer. So f prime would be x squared, and f prime of negative 4 would be 16. That's almost all you're going to have to do with the fundamental theorem today. I do want to add one little twist to it. maybe we're not just going from a to plain old x. Maybe we're going from a to some function of x. Well, if that's the case, so we're not going from a to plain old x, we're going from a to some function. Well, if that's the case, then you just have to do the chain rule. Just like we always do, if we know the derivative at x and we want to figure out the derivative of f of g of x, then we have to apply the chain rule. So this is a chain rule situation when our limit of integration is not just a plain old x, but it's a function of x. So we'll try this one. We have f of x is equal to the integral from 3 to root x of e to the t. So this is not just an integral from 3 to plain old x. So when we take this derivative, we're going to have to do the chain rule on that. So we're going to get e to the leave the baby alone times the derivative of the baby. And now plug in 4, so we have f prime of 4, we have e to the 2 times 1 over 2 times the square root of 4, which is 2. So this would be e squared over 4. Last one, and you can try this on your own and then unpause to see the final answer. All right, so f prime would be tangent of leave the baby alone times the derivative of the baby, and now we're going to plug in our numbers. So we have tangent of pi over 4 times 2 times square root of pi over 4. Tangent of pi over 4 is 1, so this derivative would be 2 root pi over 4. Okay, that's the fundamental theorem of calculus. Oh, there's one more thing I meant to tell you. This doesn't matter. Doesn't matter what this number is. This number makes no difference whatsoever. And the reason it doesn't matter is I kind of think of that as like the y-intercept. So it matters when we're figuring out the value of big F, but when we're trying to figure out the derivative of big F, it doesn't matter because the slope, that's not going to change the slope. Our starting point is not going to change how quickly our area accumulates. It only changes where we start counting area. It doesn't change how quickly the area accumulates under that function. Okay. Have a good day.